seminario extraordinario en donde aprovechamos la visita de Pablo al Centro Universitario de los Lagos de la Universidad de Guadalajara, que tiene un evento especial, y Pablo gentilmente se ofreció a venirnos a dar la plática que hoy ofrece. Pablo es un amigo de muchos años, no solamente de un servidor de ustedes, sino de Abundio, de Manuel de la Torre, que está allá atrás, de muchos de nosotros que hemos estado haciendo cuestiones de metrología óptica ligadas a pruebas ópticas no invasivas. Y es para mí un singular honor, Pablo, tenerte aquí y que me hayas dado la oportunidad de presentarte, porque sé lo valioso que es tu contribución al campo, además como persona, una magnífica persona. Pablo es alumno de Guillermo Kaufman, no sé si le suena por ahí el nombre de alguno de ustedes, pero Guillermo también es una de las personas de los iniciadores en Argentina, si no es que el pionero en Argentina en cuestiones de óptica no invasiva, ¿no? Y en el fenómeno del espectro y de moteado. Y pues Pablo tiene 20 años de experiencia en óptica, en metrología óptica y en particular en pruebas ópticas no destructivas. Tiene un doctorado del Instituto de Física de Rosario, que lo realizó ganó su doctorado en el 2002, y desde el 2002 está en el departamento de Ingeniería Mecánica de la Universidad de Loughborough en Inglaterra, y ahora es un reader, que es un pasito antes de convertirte en profesor, ¿no, Pablo? Para nosotros realmente ese tipo de títulos no nos dice más que la valía que tiene Pablo en la cuestión de investigación. Pablo es un coinventor de la interferometría hiperespectral, que tiene que ver con la versión de interferometría en luz blanca de un solo disparo. Y ahora la interferometría cobra una relevancia especial, Pablo, con el Premio Nobel 2017 en LIGO, para aquellos que en muchos lugares dicen que la interferometría y todo lo que tiene que ver con la interferometría, incluyendo las pruebas ópticas no invasivas, ya no se hace nada, de investigación básica. Bueno, pues lo único que se hace son puros premios Nobel, ¿no? Entonces, eso un poquito a manifestar la importancia que tiene la interferometría y las pruebas ópticas no invasivas. Pablo tiene diferentes intereses hoy día, entre ellos la colaboración muy particular con la industria. En Inglaterra es algo que se da de manera cotidiana, de manera natural, y está colaborando para un par de compañías en el desarrollo de instrumentos para Phase Vision y para Range. Y tiene, me imagino que durante la plática o al final vas a decirnos algo sobre tus investigaciones, lo que estás investigando hoy día, ¿no? Si gustas. Entonces, ¿cómo te gusta que te interrumpan conforme vas dando la plática, o nos quedamos al final, Pablo?
Absolutely, brilliant. Yeah, I'm happy.
¿Tú estás feliz con lo que?
I'm happy to have questions at any time, so you don't have to remember them. Yeah.
Okay.
Are you happy? Can you hear me at the back? Is that okay? Or is it better if I use a microphone? A little bit better, yeah? Yeah, it's okay. Thank you so much, Fernando, for your kind introduction. It's a pleasure for me to be here. I've been in Syria for the first time 19 years ago. I came for 3 months to work with Abundio as part of my PhD. Have very good memories and made very good friends. So what I want to talk about today is how to measure surface shape in a single shot. Okay? So recording all the necessary information about positions of different points on the surface and another information necessary to determine the height at that point. Okay? What I'm going to do is first to show you where Loughborough is. This is Loughborough in the heart of England, between Nottingham, Derby and Leicester. It's a small town, probably 150,000 people living there. It has a very nice campus. It's a very big one of the biggest in Europe actually. And it's expanding. In terms of engineering, there are 4,000 students and about 200 staff in our university, with over 30 postgraduate courses, 500 PhD and master degree students, and some very nice labs. The university has received some Queen's anniversary prizes in 7 occasions, and 4 of them related to engineering. Yeah? Aerospace, automotive, optical, vehicle, and high-value manufacturing. In terms of what engineering degrees are offered, they are related to aeronautical, automotive, chemical, materials on one side, then civil and building related to basically civil engineering, and then the Watson School that combines mechanical, electrical, electronic and manufacturing engineering. Yeah? It's been basically expanding and gobbling other departments in the last few years. So, and that's an aerial view. That's the Watson School, the old building, new one. That's civil engineering, aeronautical. This is material, aeronautical and automotive, and the physics department. Okay. So if you want to visit, you're really welcome to come to Loughborough. So, about the top. So the motivation is, I want to go through that, what motivates this approach. I want to talk about how to do measurements of the surface form, surface height in a single shot, just single exposure time of a large photodetector array. Then I will explain a different approach that we implemented to improve and overcome some limitations of the first idea. Yeah? I will have a look at the performance of that and we'll draw some conclusions. So, in manufacturing, it's very common to have machines like this, these coordinate measuring machines, CMMs. Yeah? They are usually a tactile probe, so we just touch the part, and for each point we'll measure X, Y, and Z coordinates. Yeah? They are very useful to, for example, check for the dimension accuracy after manufacturing. Are the dimensions the expected according to the design? So these take forever, okay? Because you have to basically touch. It's basically an artificial finger around the part. Full field optical measurement, it might be, many of you here are familiar with fringe projection, structure light, illumination, to measure shape without touching the part. Yeah? And each pixel in your in a camera, basically you have a camera, a projector, the projector, that projects fringes on the part. They get distorted. By looking at the distortion, you can work out the 3D shape. But these are technologies that work for large dimensions, okay, to measure shape. Yeah? But when the problem becomes measuring the roughness, so these are not good anymore, okay? Because we are talking about micron scale changes in shape. So for that scale, let's say 20 microns or 20 millimeter, the current method of choice for industry is a coherent scanning interferometry. It's also known as scanning white light interferometry. It's basically using an interferometer with white light. Yeah? And typical instruments cost about £100,000. Typical scan rates, and I'm going to describe how they work, but it takes about 1 second to scan 150 microns in height, along the height axis. Applications. Flat panel displays, photovoltaics. In the semiconductor industry, it's used to measure the shape of silicon wafers. Micro electromechanic chips or MEMS. Reel-to-reel micro patterns. So there is a trend now to manufacture micro pattern, for example, electrodes, meshes, or structure on a reel-to-reel. Basically, you have a cylinder, you imprint that on film, and very quickly you basically print very complicated structures. And they have a lot of use in photovoltaics, thin film photovoltaics, for example. Okay, so these are a few examples of surfaces measured at that scale, yeah, in the tens of micron scales. And it's important to measure the shape because usually the geometry of that topography there is related to the function of the surface. Yeah? The roughness may be linked to leaks or squeaks, noise, friction, wear, appearance of the part, and also noise, vibration, feed, adhesion, and many others. Okay, so there are many different drivers in the industry that found like a good tool in coherent scanning interferometry. So how does it work? Basically, imagine that we have a microscope here at the top, and this is an interference objective. It's also called a mirror objective. Okay, this is our object. In this case, it's like a spherical surface, can be a lens, and we have a white light source. Okay, it's a low coherence source. The reference beam comes from the top. Is reflected on a partial mirror. Here, this is all integrated within the same objective. Yeah, within the microscope objective. It's reflected up to a little spot, is a metallic mirror here, and it comes back and goes into the microscope, okay, to the image plane on the camera. Yeah? So that microscope will be capturing an image. And the other, because it's a partial mirror, we have light illuminating the object and then reflected back into the interferometer. So these two beams interfere, and this is what the camera sees. Yeah? This is what it sees for different positions of the objective. Yeah? So if you move this up, for example, we will see this first. So we have, let's say that the optical paths for the reference and the object beam are matched, where we see a good modulation of the interference fringes. Okay? So if we move this up, then we'll see the modulation is now good at that plane, and then if you keep moving it up, it will be just good at the top. Yeah? So if we look at 1 pixel as a function of time, as we move this objective vertically, then the signal, the intensity signal, will look something like this. Okay? So that 0 is the 0 optical path difference between the object and the reference. So each pixel will have something like that, and this will be at different points depending the shape of the surface. So how do we determine where the surface is? Just by looking at the maximum of that envelope would be enough. Yeah? But if you want to have even a better accuracy and precision, then you can look at the face of that fringe pattern inside the envelope. Yeah? By looking at the face, you can have about a few nanometers, yeah? Precision. Okay, that's how it works. Because it is a scanning system, it takes time to move that, so you have to, for each position of the microscope objective, you need to capture an image. So you end up with hundreds of these, yeah? Lots of things. And here we have an example of the surface. In this case, it's not polished, it's just a metallic surface, and you see the fringes going through, cutting through, yeah, we see the intersection of that fringe pattern. That's called the coherence gate. Yeah, it's called a gate because we only have interference signal within that very short or thin plane of light. Yeah? It's equivalent to having like that. Yeah, that basically this is symbolizing the surface, and we just scan the fringe pattern. Yeah, that's the intensity of my fringe pattern. We'll have, you know, planes of bright and dark light distribution here intersecting the surface. That's how it works. Now, that takes time, and that makes it not very suitable for an online production. Let's say for production. Vibrations are a problem, you know. You'll have holographic tables in our labs. If you don't, the vibrations blur the fringes, we can't see anything. So it's the same here, yeah? It's low coherence, but we're searching for those interference fringes. So vibration means that you have to take one sample. Let's say you're producing thousands of parts, yeah? Hard drives, yeah? Or micro lenses for mobile phones. You have to take a few samples, take them to the metrology lab, measure some of them, and come back and say, okay, they look all right, keep producing. But 99% of the product haven't been tested. Okay, so there is a lot. There are lots of mistakes. Right? So quality control is not good enough. So the questions that we posed was: is it possible to measure that in a single shot? So is it possible to record basically all the interferograms in a single time? Yeah, at the same time. You quickly realize that there will be trade-offs, yeah, because there is a lot of information in this stack of interferograms. Yeah? You have high spatial resolution, and we also have lots of different frames to scan a large height depth range. So it is possible. I'll show you how it could be done, and we have to accept a few trade-offs. So this is the first implementation that we came up with. So how does it work? We have here a superluminescent LED. So it's a broadband source. It works in the infrared. The central wavelength is usually 840 nanometers. And the bandwidth is about 50 nanometers. Okay, it's a lot broader than an LED, yeah, and a lot brighter. That's why it's called SLED, superluminescent. So we have a Michelson setup. Well, make a Linux. Yeah, the difference between a Linux and a Michelson is that in a Linux you have two imaging lenses here of the same property, so that they are matched. Yeah, in terms of optical path and dispersion and all that. So we have the reference mirror, the surface that we want to measure. We have a step here, for example. And so these two beams recombine and go into a spectrometer. Yeah? That's basically how you can understand the basics architecture of the instrument. So you have an interferometer on one side as the input, and the output of the interferometer goes into a spectrometer. Yeah? And that spectrometer is simply here, a diffraction grating in a vitro condition, and a lens, and a photodetector array, CCD cam and CMOS detector. Yeah? So notice these lenses, for example, L2 and L4. Yeah? If this is at the focal plane of L2, they have collimated light, and then L4 will focus and form an image of my object at the camera, yeah? At the photodetector array. But because we have a diffraction grating here, we will have a spectral spread of all the colors, because this is broadband light source. Yeah? So you'll see little images of the surface all spread continuously along the dispersion direction of the spectrometer, the wavelength axis. Okay? Just a diffraction grating. Yeah? If you see through a diffraction grating a star, you will see, let's say, a line, yeah, with all the colors. Yeah? That's exactly what it looks. So for each point in the object, you will have a line on the photodetector array. But now, it's a problem because all is blurred continuously along this wavelength axis. The solution to separate these in independent images or sub-images is to add an interference filter here, an echelon, yeah? But basically it's a comb, a frequency comb. It will separate, it will attenuate wavelengths such that we can have a gap between these little images, okay? The transmission function of an echelon is basically just peaks of transmission, yeah? Equally spaced in the wave number axis, okay? In the frequency axis. Is that okay so far? Any questions? Can you follow the idea so far? Yeah? Good, okay. So with that in mind, so what we have to do now is, let's see how it looks, what the camera says. Yeah? So this is what the camera says, okay? It's all black. Yeah? And we have these little images there in the middle. So this is diffraction, grating, dispersion axis. So the wavelength is changing in this direction, okay? And these little things are the images I'm capturing. So let's have a look at this. Let's zoom in and we see 3 different images, okay? Each of these corresponds to a different wave number, okay? Wave number is 2 pi over lambda, yeah? It's in low coherence interferometry, we always work in wave number. We tend to avoid thinking in terms of wavelength because everything is linear in wave number, but not in wavelength, okay? So it's very convenient to always work in K space. K 2 pi over lambda. So we have, for different K values, wave numbers, we have different images. Okay? So if we remove the echelon, we'll see only a bright line across, yeah? Like smoothly spread. Okay, so let's take all of these images and stack them together. We'll need to basically crop them from the image and put them one on top of the other in a data volume. Let's say we have X, Y. These are the X and Y axis. And this is the K axis. So we take this and we put them one on top of the other. Yeah? Different K values. That's the K axis. So now, if we look at one pixel here of the field of view, let's say the blue pixel, that corresponds, in this case the object was a step. Okay? So the blue pixel is closer to the zero delay line of the interferometer. Closer, so the optical path difference for that point relative to the reference beam is shorter. Yeah? So if we look at if we follow the intensity of the pixel along the K-axis, we see a modulation. That's a modulation intensity. Yeah? And the frequency of that modulation is proportional to the optical path difference I mentioned. Okay? So to the height of the surface. Yeah? So if you take another, this is the height, the other part of the step. Yeah? This is further from the reference zero delay line, and it will give us a higher frequency. Yeah? So by doing a simple Fourier transform of that, if you do that for every pixel, we can find that the frequency is proportional to that distance, to the height of the surface, and we can do that for all the pixels and map, and this is the step that is measured. Okay, that's the top of the step, closer to the reference beam. That, let's imagine there is a plane at the top here. So that distance is short for this one, low frequency. It's long for this one, high frequency. It's very simple. The frequency is directly proportional to the height of the surface. It has many problems. Okay, only 2% of the pixels are used. Okay, so it's all wasted really badly. Okay, and that's a big problem. Then we need to do sub-image registration. That means that when we cut all the little images, then you have to put them on top of each other very carefully, because you don't want to then be mixing pixels that correspond to different points on the surface. So, and that has certain challenges as well, and errors creep in. So, it has a reduced throughput. Throughput is how much light you get through your system. And an echelon, the filter, basically has to be designed with a finesse so you are able to separate these individual images. In this case, the finesse of 15, which means that you end up with only 1 in 15 of the original power of your source. Okay, so you waste a lot of light, basically only struck by the filter, by the etching. The spatial resolution is not impressive at all. So you can see we're at 19 by 11 pixels. Yeah, but it's proof of principle. Yeah, just to see if it works at all or not. And then the unambiguous range was more, 350 microns. What is that? The unambiguous range is how far, or what is the height, the maximum height that we can measure before we have that the face rupts. Okay, and it can be calculated. That we don't need to worry about that too much. But if you want to measure steps of 0.5 millimeter, and you can't, basically that's what it means. So the second approach, I'm going to explain a different system now that was inspired by really what astronomers do. Yeah. So it happens that astronomers have been looking at rotational speed of galaxies for a long time. Yeah. And a good reason for them is just to try to match observations with dark matter models. So the observed profile of the rotational speed of galaxies is like that. Okay, it doesn't get faster as you get further from the center of the galaxy. It kind of plateaus here, and it just basically constant. It doesn't vary with the radius. Yeah, and that means that you need to add something to the models, because this is what you observe, and if you don't put dark matter into the models, this is what happens. Yeah, so they need to add that to match the data, basically. Yeah. And how do they measure rotational speed of galaxies? Yeah? And they do this by looking at the redshift, yeah, of light, using Doppler effect. Let's say that this galaxy is rotating like that. Okay, so this part of the galaxy going further, and so if it's going away from us, we'll have a red shift. If it's going towards us, we'll have a blue shift. Changing the wavelength, yeah, Doppler shift. And to do that, they have to basically come with a spectrometer and measure what happens with this part of the galaxy. Look at what is the redshift, what happens in the center, and so on along the radius. Okay, so they have to use a spectrometer to do that, and this is what they've done. Yeah, they designed Tiger. This is in a paper 1995. It's for, well, that's the French for it, okay? And they call it Tiger. Sometimes astronomers like to put, catchy names for the instrument. This was called Tiger because it shared the cage of an instrument that was called Puma, yeah? And the cage is just the rig, yeah? Basically the structure where they put the instrument. It's cool. So how does it work? So let's say that we have here a very expensive telescope, okay? And that's the focal plane of the telescope. Yeah? Here they have different optical systems here. We don't need to worry too much about this, but let's just follow what we have at different parts of this. Here we have an image. That's not a very impressive image of the galaxy, yeah? But that only could print in black and white. Right then. But that's a galaxy. Yeah? And then they image that with an enlarger onto a micro lens, a lens array. Basically, the lenses here that we're using, they were a few millimeters. Yeah? Telescopes can project an image on the telescope image plane of that size. Okay? So they put a lens array, but it was about this size, yeah? With hundreds of lenses. So behind the micro lens array, or the lens array, they have spots. Okay? A focal spot of each lens. Right? So each lens is sampling one small region of the image plane. It's a spatial sampling, okay? And it's designed in such a way that the point spread function of the telescope is going to be sampled by a few lenses. You need between 4 and 5 lenses in order to really properly sample the signal so you don't lose spatial frequencies and resolution. You wouldn't like to lose resolution if you have a very expensive piece of optics, like the 4 optic, yeah? So basically what you have here at the lens array is a plane wavefront. Basically you have plane wavefront. And you have these spots at the focal plane of the lenses. So these spots, then you put a dispersive element here, which is a combination of a diffraction grating and a prism. And what you get here at the CCD plane, this is imaging lenses, you convert each dot into a line, and that's the spectrum for that point. Okay? And if you then look at the spectral content, they could decide, okay, it's red shifted, blue shifted, and so on. Okay? The trick here was to rotate the diffraction element here, the dispersion element, axis relative to the arrays, so that you don't have an overlap here. This is a zoom-in version of this, okay? You don't have an overlap of these lines, yeah? Let's say if you rotate them, we just overlay one on top of each other. So by carefully adjusting it, it's possible to pack lots of spectra on the same detector array, okay? So you can see now it's quite attractive because you're using the load, you're using the 2D sensor that you have, okay? Alright, so we came back to the lab and say, okay, we have our linear interferometer, and now we're going to change the spectrometer side of it. Okay, this side is exactly the same as before, it's a slightly different lens here, and that's a spectrometer. So if this is the object, that's my reference beam, that object is imaged by these two lenses onto this plane. And here we put a micro lens array. Here we're talking about micro lens array. Each lens is 100 microns diameter. Yeah, and we have, let's say, 100 by 100 of that in a square centimeter. That's the pupils plane, where we will have the spot due to each lens. And then we have these two lenses, L4 and L5, will form an image of the spot on the photodetector array, which is a 16 megapixel monochrome camera, is astronomy grade, basically 4,000 by 4,000 pixels. Okay, it's just large format. So lots of pixels, we can pack lots of spectra there. And we have a diffraction grating that will of course have 0 order, first order, -1 order. We place the grating so most of the power goes in this direction. There are two illumination schemes there that you notice. One is called two wavelengths, and the other one is broadband. This instrument needs broadband illumination to work, okay? Basically, this is a superluminescent diode, this is a fiber coupler. We can either use it in this configuration, so in this case it will go here. We have two fiber grating that will reflect two specific wavelengths, and we'll go back here into, that's number 2, that's the input to the system, okay? So when we illuminate with two known wavelengths, we can use that to calibrate the spectrum, okay? Because then you will have here some dots corresponding to the wavelength. By knowing the wavelengths, you can calibrate position with wavelength in the spectrum. And then once we calibrated that, forget about this and use the broadband, and then you can interpolate and adjust all the wavelengths around. So this is how it looks. Let's see in more detail. Here you have some parameters of the different optical elements, and this is how it works. This is what we see at different points. Yeah, that's the micro lens array, that's the spectrometer side of the system. If we have a step, imagine that we have the same step that we had before. This is the top view of the step, that's a side view. So that's a zero delay line, that's the apparent position of our reference mirror in the interferometer. That's the height of the surface relative to a certain datum. The datum is a plane that we choose arbitrarily from which we are going to measure the height of the surface. Yeah? They can be the same plane, of course. But basically, we have the height that depends on position. Okay? So this is what we see from the top. Now we are going to suppose that we use only 5 by 5 micro lenses. This is for the sake of explanation. Yeah? We have, these are the indices of the micro lenses. We tilted this a certain angle alpha to avoid that overlap that I mentioned before. After that, this is what we see at that plane, yeah? The red arrow, the red square. At the pupils plane we have these spots, okay? The focal point of each microlength. And at the photodetector array, each dot is a line, a spectrum, yeah? But because we have the reference beam and the object beam interfering on the microlens array, what we see is an interferogram, because the interference will be constructive or destructive depending on the wavelength, yeah? So this is wavelength, remember, yeah? The horizontal axis. So we have a fringe pattern there, unidimensional fringe pattern, and the frequency of that fringe pattern is proportional to the height, yeah? Here, for example, the dark gray points have a large height here, high frequency, yeah? And the light gray ones, small height, low frequency. That's all, okay? Understanding that, that's how it works, yeah? That's how depth is encoded in depth and position is encoded in a 2D sensor. So now we have all the information that we need and we can extract now height maps. So let's see, this is what the camera sees. That's one image from the camera. I think this is 2,500 pixels across, so the full field is slightly larger than that. Okay? So this is what the camera sees, and that's a zoom version in the middle for the 2 wavelength illumination. So we have for each line, these horizontal lines are the spectrum. Okay? But in this case, they look dark because you only have light reflected from the calibration rating. Yeah? Calibration wavelength. So we see 2 spots per lambda 1, lambda 2 per spectrum. We measure the position, so okay, this falls in this pixel. Here we have to do a very careful least square fitting of Gaussian functions to that spot and find the position, so we attribute the position to each wavelength, we calibrate the wavelength axis. This is where we use the broadband illumination. Okay, now we can see the horizontal line. If you take a profile here, this is how it looks like. Yeah, this hasn't been filtered or anything. There are no filters at all. Yeah, so the signal is quite good. And then we need to process that for all these little spectra. Here we have over 1,000 spectra there. So this is what we do. It's just simply a Fourier transform. Actually, what we need to do is convert marked wavelength in wave number, linearize the system in wave number, as I said, then calculate. So we are expressing this in wave number here, that signal. The Fourier transform gives us a frequency, and the peak, by locating the peak, we can locate the surface, basically. Where is the surface? And frequency is proportional to distance, so you can see it just changed the axis. Okay? And in this case, these are 800 microns. Okay, this is roughly a millimeter. Yeah, all that. So if we do that for lots of pixels, and I want to show you just some tests we've done. We have a mirror, just a flat object, and we just want to put in a translation stage, morbid 50 micron steps, and see what the instrument sees. And the instrument gives us very close figures. So that's the distance between the planes that we measure, and that's within the uncertainty of the RMS error of the instrument, which is about half a micron. Okay, about half a micron. The depth range over the root mean square error of that fluctuation here gives us the dynamic range. So we can measure, let's say, what is that? 0.88 millimeters depth with that RMS in terms of noise to determine the height. So basically we can determine about 200, just over 1800 different levels of height. Okay. So this is another test where we put a circular glass cover slip, a very thin piece of glass, used just to cover the samples within the microscope, of about 110 microns height, and you can see here the circular edge. That's the field of view that we're looking at, okay, about centimeters square. And here we have about 35 to 35 points, and all that is measured in the single exposure time of the camera. Okay? So if you have let's say, a powerful source, then you can just reduce that to, well, depending on the sensitivity of the camera, it can be milliseconds, it can be microseconds. Yeah? If you have a pulse source, you can do that at high speed as well. So it works also for rough surfaces. When you have speckle, some spectral will look nice, some spectral will look not as nice, but you can still, so the signal is, of course, affected by noise. Speckle is here the level, and you see some noise there. So what we're doing now is to try to measure the roughness as well from this, because there's enough information to capture the local roughness there. So that's it. To conclude, I want to compare this. This second system has over 40% pixel coverage in the detector. Why it's not 100%? Because we need to maintain the distance between the spectra so they don't overlap, so we don't have a crosstalk. Yeah? If we try to squeeze them too much, then we start to mix information from one point to another. Yeah? We don't want to do that. So we have 10 times the increase in throughput. That is because we don't have an echelon now, and this is just transmission. Yeah? So it's a lot more efficient in terms of light usage. We have 6 times more channels, basically the points that we measure, and an increase also in the unambiguous depth range, how deep you can go. Before we have 350 microns, this is nearly a millimeter. So now imagine that we had a pulsed illumination system and we wanted to measure surface form and absolute distance. That could be done without vibration isolation. Yeah, because a pulse source will just snap, as we do with, we use pulse laser to measure transient. Yeah, basically the pulse duration will be like flash, and the interference fringes won't blur out. It won't be integrated in the exposure time. So, and to give you an example, this is a commercial camera now. You can show 100 frames per second, 5.5 megapixels, and that could be measured with that speed. Yeah? So I think that's it for me. And thank you very much for your attention. I'm very happy to answer your questions now.
Thank you, Pablo. Thank you very much. Thank you. ¿Te hacemos las preguntas en español o en inglés?
Como quieran. Disculpe, pero si empiezo en español, no hay
vamos a empezar acá y luego vas a sacar con...
No, yo voy a empezar para mí.
Sí.
Vamos fuerte. Oye, una de las dudas que me quedó al principio, bueno, pues ya que presentaste los microlentes, me quedó la impresión que los tienes que alinear para que te salgan las líneas rectas del interferograma, ¿no? Y puedas de ahí cerciorarte que lo que tienes ahí es dispersión en esas de ahí. Sí. Cuando tienes una superficie rugosa, ¿cómo haces para hacer esa alineación?
El ángulo de esa línea no depende de la superficie.
Ajá.
Independiente de la superficie, solamente depende del ángulo relativo entre el microlens array y el eje de la rejilla de fracción. ¿Sí?
O sea que eso lo puedes aplicar a cualquier superficie una vez que hiciste ese matching y estuvo.
Exactamente, sí. Si pongo una superficie especular, estos efectos se ven muy bonitos, ¿sí? No hay, o sea, porque todos tienen luz. ¿Sí? Pero si pongo una superficie rugosa, voy a tener un speckle pattern aquí en el microlens array. Entonces algunos microlens van a tener un espectro brillante, otro oscuro, y no voy a ver modulación o señal en todas ellas. ¿Sí? Pero eso depende de cómo uno ajusta también el tamaño del espectro relativo a los microlens.
Oiga, otra pregunta más por curiosidad. Como mencionaste a los astrónomos desarrollaron un lenguaje basado en PERL, que es PDL, Perl Data Language, que es exprofeso para hacer transformadas rápidas de Fourier de este tipo de datos.
Ajá.
Yo lo utilizo para resolver las ecuaciones de Maxwell, es otra aplicación, ¿no? Pero no sé cómo hagan, qué software usen para hacerlo, y si no, PDL es gratuito y es una excelente opción, porque tú puedes meter toda tu hilera de datos, por así decirlo, toda tu matriz de datos, y en un paso hace la transformada rápida de Fourier.
Ajá. No lo conocía.
Si les
No lo
interesa.
conocía. Sería bueno mirar un poco más cerca. Lo hacemos en MATLAB, nada extraordinario en ese sentido. Ahora que sí hay que tener mucho cuidado cuando uno hace la transformada rápida. ¿Dónde está? El secreto es determinar con precisión cómo se hace, cómo se encuentra el máximo de ese pico. Ahí, ahora, los circulitos aquí están mostrando, porque esta no es una señal continua, ¿sí? Tengo circulitos aquí también, son las distintas muestras, por los distintos píxeles que tiene la cámara. Estas son las frecuencias discretas que mide la transformada, ¿sí? Rápida de Fourier. Y esta, la línea continua, se utiliza la discrete Fourier transform, ¿sí? Y es un algoritmo que desarrolló John Huntley en los 90 para analizar la frecuencia espacial en fotografía de espectro, spectrophotography. Se puede localizar el máximo del pico con subpixel precision en este caso, ¿sí? Básicamente se encuentra no el número discreto, no se encuentra el máximo así con un very simple search, pero se encuentra el valor real, ¿sí? A real number, basically, the fractional number. That's it. But we didn't have the problem of having to process that quickly.
Abunde.
Pablo, muy interesante tu práctica, gracias. Nada más, yo me perdí un poquito, a lo mejor, en el primer arreglo tenías un etalón, decía que mostraba las diferentes longitudes de onda en uno de onda, y en el siguiente ya no existe.
¿El etalón?
Bueno, no sé, a lo mejor me perdí un poquito, pero ¿qué es lo que hace en el siguiente arreglo que muestre las imágenes en uno de onda?
Las imágenes ok. So, tu pregunta aquí es, acá está claro que el etalón te permite separar, ¿sí? Y el etalón te va a dar imágenes que cada una corresponde a un número de onda y hay una separación constante entre el término del delta K, entre ellas es el mismo, ¿ok? Entonces en este caso es fácil, no hay que hacer nada, ¿sí? Se acomodan las imágenes así. Después de ese procesamiento que ya describimos, listo, ¿sí? El otro es diferente, el otro es longitud de onda, ¿sí? En este caso tenemos el espectrómetro y acá, vamos a esta imagen, esto es longitud de onda, ¿sí? Esto es longitud de onda, ¿sí? Entonces lo que hay que hacer es convertir esa longitud de onda en K, y para eso utilizamos las dos lambdas de calibración, las dos longitudes de onda de calibración, que se conocen hasta unos picómetros, ¿sí? Entonces yo puedo ir a hacer el 2pi sobre esas lambdas para dos puntos del espectro y después aproximo, según la ecuación de la rejilla o una aproximación lineal, para convertir todos los puntos del espectro en K, en número de onda y dato, ¿sí? Ahora, lo ideal sería hacer resolverlo exactamente utilizando la dispersión de la rejilla y como depende del ángulo con la longitud de onda, pero es mucho lío, no vale la pena, porque haciendo una aproximación lineal uno tiene un error de 8% del píxel nada más. O sea, si uno tiene que atribuir una longitud de onda al centro de un píxel, hacer la aproximación lineal no me corre del píxel, está dentro del píxel por un 8% de su ancho.
Mauricio.
Comentas que uno de los propósitos de hacer esta modificación o de las ventajas con respecto al white light interferometría es porque lo quieren usar para ambientes industriales, donde obviamente el white light tiene la desventaja de vibraciones y muchos otros factores externos, como casi toda la interferometría. Pero por ejemplo en este caso que se utiliza esta aproximación, el problema de las vibraciones o el problema de la inestabilidad del sistema no se trasladaría, por ejemplo, a las microlentes, y entonces una pequeña fluctuación a lo mejor ya no lo tienes en interferometría, pero a lo mejor sí lo tienes en la alineación de las microlentes o de la rejilla después de las de las microlentes. ¿Cómo están lidiando con ese tipo
Ok,
de
sí,
cuestiones?
buena pregunta. Teníamos ese miedo también. ¿Qué pasa? ¿Sí? Esta cámara es una cámara de astronomy grade, basically. Necesita estar, ¿cómo se dice? Cool, enfriada, y tiene también 4 ventiladores que andan constantemente. La vibración de esos ventiladores no provoca ningún problema en las franjas de interferencia. ¿Sí? Estuvimos pensando si podía afectar la localización de estos spots, ¿sí? Porque si tengo vibraciones, por ejemplo, relativas entre las microlentes y la cámara, estos spots tendrían que moverse encima de los píxeles, ¿sí? Pero esa variación no la podemos detectar en esas condiciones, y con la mesa holográfica no inflada, ¿no? O sea que es bastante robusto en ese sentido, ¿sí? Si por ejemplo tenemos la cámara corriendo en continuo y uno mueve, uno puede ver cómo esta franjita se mueve. Si uno acerca el objeto o lo aleja, tengo más o menos franja. Eso es lo que pasa.
Desde el punto de vista del espectro de Fourier, ¿tienes algún corrimiento de la información? Por ejemplo, en la última diapositiva, la componente 0 estaba en el pico un poquito más alto. Eso se debe nada más a cuestiones de ajuste. Sí. Hay otra que mostraste que se ve un poquito más alto con respecto al pico que quieres ver.
Sí.
Y es casi del mismo nivel.
Sí. Ese es muy buen punto también. Hay que detectar dónde está la superficie, ¿sí? En este caso, esta transformada de Fourier es de esa señal, ¿okay? Se puede utilizar un método que lo estamos utilizando ahora, que es extraer la envolvente de esto y básicamente sacarle esas componentes de baja frecuencia para atenuar ese pico de ahí, que sabemos que están, sobre todo cuando hay espectro, ¿sí? Porque hay más ruido. Entonces empieza a competir la altura de ese pico con esto. A veces puede ayudar saber más o menos dónde está el pico mirando a píxeles vecinos, a microlentes vecinas, ¿sí? Pero es algo que sí hay que tener en cuenta, ser capaz de discriminar cuál es el pico. Otra cosa que no mencioné es que si yo, por ejemplo, muevo la superficie hacia el término del DC y pasa hacia el otro lado, uno no puede, es ambiguo el problema, ¿verdad? Es como cualquier interferómetro en máquinas. Sí, no puedo determinar si estoy por detrás o por delante de mi plano de referencia.
Carlos.
Sí.
Hola, ¿qué tal?
No, Pablo, el ancho del etalón lo varía según la rugosidad del material móvil.
¿Cómo?
El ancho del etalón.
El espaciamiento del etalón lo varías.
¿Cómo diseñamos el etalón?
Cambias el etalón dependiendo de la rugosidad del material móvil.
A ver, el otro Z, sí, el etalón. El etalón se diseña, está aquí, ¿sí? Este etalón no tiene que ver con la rugosidad del objeto. Vos estás pensando en la rugosidad del etalón.
Supongo que más ancho el etalón, las franjas estarán más.
Ok. Bueno, pero esas franjas no están, no hay que imaginar las franjas aquí como si estuvieran en una coherence gate, ¿okay? Porque acá el objeto recibe iluminación de todas las longitudes de onda que vienen del etalón, de todos los modos que pasan a través del etalón. El espesor del etalón se diseña de tal forma que tengamos una separación entre los picos, ¿sí?, de transferencia del etalón suficiente para separar estas imágenes aquí. Si por ejemplo yo diseño un etalón más finito, de tal forma que los picos estén más separados, entonces voy a ver una imagen aquí y la otra mucho más lejos, entonces puedo ver un campo más grande, ¿sí? Pero al mismo tiempo, el delta K, la diferencia entre los picos del etalón, se agranda, y eso hace que se reduzca mi rango máximo de profundidad que puedo medir. Hay varias variables que están en interplay.
Enrique.
Bueno, las muestras, bueno, hay instrumentos obviamente ya en el mercado hace mucho tiempo para medir rugosidad ópticamente, etcétera, etcétera, ¿no? De hecho, originalmente Waiko fabricaba estos tipos de instrumentos con luz blanca y de hecho el instrumento estrella de la compañía, lo que más se vendía, ¿no? La pregunta es, cuando iniciaste tu plática, lo que me hubiera gustado saber es ¿qué resuelve esto que no resuelvan los otros? Esa sería una pregunta, ¿no? Y la segunda pregunta es si han considerado un método que se conoce como el método de fracciones, ¿cómo se llama? Exactas o algo por el estilo, en que con 4 longitudes de onda tú puedes medir, extender increíblemente la profundidad. Por ejemplo, el que se usa para medir calibrar algas en metrología. Usas 4 longitudes de onda y te quitas la ambigüedad. ¿Sí? Puedes decir, puedes llevarla a milímetros o a centímetros y medirla absolutamente. Entonces, estas dos cosas.
Okay.
¿Qué resuelve esto? Porque
La primera pregunta.
Sí.
¿Qué resuelve?
Sí.
Mencioné en la introducción,
Sí.
pero lo puedo mencionar ahora. Este tipo de instrumentos, la compañía que estaba interesada en esto, Remington, ellos fabrican, diseñan, inventaron este tipo de probes,
Sí.
de touch probes.
Sí.
Y también las perfeccionaron hasta un punto que fue muy rápido, es muy lindo ver estos robots tocando, ¿no? Y tienen un proyecto para cambiar esta probe táctil por una óptica. ¿Okay? Entonces la idea, bueno, si queremos cambiar esto por una prueba, por un sensor óptico, ¿sí? Lo que nos imaginamos, bueno, sería bueno tener un sensor óptico que puede darle un pequeño campo visual, ¿sí? No tiene que ser muy grande, por ejemplo, unos 10 por 10 milímetros, por ejemplo, unos cuantos milímetros cuadrados. Y ese sensor se aproxima a la superficie, lo mide, guarda los datos y después se va acercando y va haciendo, como está montado ya sobre un brazo robótico, lo único que tiene que hacer es cambiar el sensor. Y nuestro plan era diseñar, primero, una vez que ya funciona la idea, miniaturizarlo y poner un sensor de este tipo. Esa era la intención. La ventaja con respecto a sistemas como estos necesitan scanning. Las imágenes no podemos competir con esa resolución espacial, pero esto solo se puede hacer en un laboratorio en metrología. Pero si hay que ver, por ejemplo, un problema que tiene de producción de muchas partes que hay que verlas todas es producción de alas de turbina, turbine blades, por ejemplo, para motores de compresores de jets. Y en ese caso, por ejemplo, es importante no solo la forma correcta del blade, sino también la textura de la superficie. Hay microcracks, hay defectos. Entonces un sensor óptico podría usar. Y lo que era atractivo es decir, bueno, si se puede utilizar, y si es robusto frente a vibraciones, entonces lo puedo utilizar en la línea de producción. Hay que pasar todo a un laboratorio de óptica o una pequeña muestra de todo el laboratorio de óptica.
Sí, nada más que los campos que tú enseñas siempre son de micrómetros. Yo me imagino unos álabes de turbina con una...
Son de este tamaño.
¿Qué?
Los álabes de turbina, los que hablo no son los que se ven por fuera del avión, son los que tienen distintas etapas de compresión dentro del motor.
Sí.
¿Sí? Y son más o menos de este tamaño.
¿Cuántas muestras necesitarías?
¿Cuántas muestras?
Sí, o sea, ¿cuántos campos necesitarías ahí? Miles.
Sí, tengan en cuenta que estos son proof of principle, ¿okay? Este no es un prototipo para esa aplicación, ¿sí? Si quisiéramos hacer un prototipo para una aplicación real como esa, el proceso involucra el Product Development Cycle de la compañía, que en promedio son 9 a 10 años, ¿sí? Entonces involucra ingenieros del team de producción, del team de diseño, del team de data processing y todo eso. Es mucho esfuerzo. O sea, esto es TRL 1, TRL es Technology Readiness Level. Que cuando ese TRL es una escala que se utiliza para ver qué tan próximo está una tecnología a producción o a fabricación, ¿sí? Y va del 0 al 9.
Lo conocemos perfectamente porque
Claro.
en México nos quedamos siempre en ese nivel. Sí,
The TRL 4 and 7 is the value of depth. They call it the value of depth. Because you are very good at TRL 0, 1, 2, 3, and nothing. And then some products. Yeah? But it's very difficult to go from innovation or from proof of principle and scientific idea to make them into products. So that process is of innovation. Yeah, it's hard. And this is TRL 1, 2. Okay, just prove it. Does it make sense? Is it theoretically possible? Yes.
Nada más una pregunta. ¿No?
I need to answer the second question. And your second question was a very good one. And it's related to the fact that you don't need to use too many wavelengths to detect how far a surface is. Yeah? You can use, let's say, 2, 3, 4. That's the concept of synthetic wavelength. Okay? You mix 2 and the depth measurement range, you extend it a lot. So it's inversely proportional to the distance between your wavelengths. Okay? It's very good. And I think you mentioned the method of, I can never remember, it's just the exact fractions or something like that. But it's a method that was developed by Dave, what's his name, from Leeds University. A colleague from Leeds University. Yeah, the method is basically a clever way of choosing your wavelength to, instead of using all of them, using some of them. Yeah, so you don't need to measure to have redundancy in your system. Yeah, that's what we're planning to do now. But not in a system like this, but in a wavelength scanning interferometry. So if you project, for example, if you have a tunable laser, and you project a wavelength, and then another one, and then you have, let's say, an exponential sequence, so you find the right sequence of wavelengths, you can determine where the surface is in an optimal way. Yeah, that's a very good approach. But I don't think it will work in something like this when you are already detecting all the pixels. Okay? So if you want to use that method of certain wavelengths, and use all of them, so you already have them. Yeah, so there wouldn't be any advantage of using that method with that data.
Gracias. Tenemos quizá tiempo de una más, una pregunta más para Pablo y luego cerramos con algunos comentarios.
Filosofando o una cuestión retórica que te comentó Enrique, que ya lo dijiste, que se queda en el proof of principle. Aquí en México se cuestiona mucho por qué nunca se llevan los proyectos a nivel 8, a nivel 9, a un prototipo. Bueno, pues ¿cuál es el porcentaje de éxito, por ejemplo, en Inglaterra, para todo este tipo de investigaciones que se hacen y que se quedan nada más en los niveles 0, 1, 2 y ya no permean más allá? O sea, ¿tienen el mismo problema o su tasa de éxito es prácticamente... Y no por eso las compañías dejan de perder interés en invertirle, ¿o sí?
I don't think I can give you a number in terms of success rate. Yeah, it's very hard. It's very hard. So we work with these companies for years, and we didn't get to that point. Okay, why? Because the company decided at the end, and there's a long process that you have to go through, which is you need to protect the IP, you need to patent the idea, and that's expensive. Yeah, it takes a lot of your time. Yeah, but if you don't have a patent, nobody cares. Yeah, because a company will like to say, okay, well, that's your idea. Okay, have you got a patent? Is it protected? Because if it's not, if it's been published, then I cannot guarantee that we will have exclusive use of the idea. Yeah. So what you have to do, basically, the process is you patent, and then you license the patent to a company that has technology and the capacity to take it to a product. Okay, that's the approach that we follow. I said, okay, let's do that. It took more than 2 years to negotiate the license agreement. Okay, royalties and all that. And after that, the company board of directors, this is a company, Renishaw, that invests 15% of their profits in research and development. 15%. This is a private company. That's extraordinary. Okay? So they have the resources. Yeah? And they decided that actually another application that they wanted for this was to look at an accessory for microscopes. Okay? Because that technique can also be used to look into materials, 3D, OCT, optical tomography. In that example, I just showed you a surface, but if you have a skin, for example, or a semi-transparent sample, you can see through. Okay? So we have very nice ideas as to how to build an instrument for an accessory for microscopes. That was a plan. And suddenly the board of directors decided that we changed our minds, we'll put more money on this other area because, yeah, they are strategists. They try to assess where are more commercial opportunities, and that collapsed. And now we're back to around zero. Yeah. So what you have to learn is don't be disheartened. Just keep working. Yeah. You learn a lot. Don't get cross with the industrialists because it's just business. Yeah. It's not personal. Yeah. It's not that the idea is bad, but it doesn't have a place in the market. And if you want to take it on your own, you don't have the resources because it would cost millions of dollars. Yeah. In that case, to take something like that from that point to the point that you want to see it is 9 to 10 years and several million pounds. It's a huge investment. Yeah? So, again, in the UK, Europe, you have thousands of ideas, millions of ideas. Some of them will find a way. Usually the most effective way of taking an idea to a commercial product is spinning out a company. I don't know how that works in Mexico. Is it common to spin out a company? You have an idea, you say, I'm going to make a company. Just create your own company, and then you have a great vision for a market for that. You are connected to hundreds of customers there. That's hard, isn't it? It's hard. But no, spin-out companies have that ability to shorten that time between 9 and 10 years to a couple of years, 2 or 3 years, yeah? And it has to be an organic growth. So if you ever plan to have a company, just avoid going to venture capitalist funding, yeah? VC funding. They call them vulture capitalists, yeah? Because what they want, are we okay with time? Because I don't want to overrun, yeah? They will give you a lot of money. I say, okay, 5 million, that's what happens with Face Vision. I started working for a company at the beginning. That company had lots of money from venture capitalists. Yeah, they have very clear exit strategy. That's the word. Exit strategy from a businessman means I know exactly when I'm going to get out of the business. If I don't see it growing as I expect, you're out. You will cut your funding. That's what happened. Yeah, it's very hard for a small company to have that kind of pressure in the board of directors. But a spin-out company that grows organically, just okay, you make your idea, make a small instrument, sell it to one guy, another friend. Okay, you expand slowly in the industry organically by demand. It's demand-driven. Yeah, you don't create the demand, you find it. Yeah, and that's a lot better. Yeah, and it's a less risky approach. It takes more time, but you build your company.
Pues muchas gracias. Yo quisiera concluir nada más rápidamente, antes de entregarle un reconocimiento a Pablo. Todo este tipo de cosas, yo lo veo muy positivo, pero por ejemplo yo te preguntaría, Pablo, tú sabes cuál es, si tú vas a Lloyds Bank o a Barclays Bank en Inglaterra y dices, quiero hacer mi spin-off y quiero $1 millón de pesos británicos, ¿cuál es el interest rate? ¿Cuál es la...?
They will say get lost.
Más o menos lo que dicen aquí.
Well,
Pero más o menos, ¿cuánto está el...?
It's not the way. It's not the way. I don't know. It's no interest rate. So it's not the way that businesses are funded. You don't go to the bank. You go to angel capitals, yeah, which is basically a rich guy with some ideas. Or you go to this club of rich guys, which are called venture capital. Yeah?
O vouchers. Sí, bueno, aquí todavía yo logré...
They give you the money.
Sí.
If you don't work as they expect, they don't ask for the money back. But your business is there. Okay?
Sí.
So it's not a loan. It's not a loan. It's an investment for them with the risk. It might not work. They know the risk. Put the money, doesn't work, out.
Pues es muy... A mí me encanta este tipo de cosas porque primero estamos muy en la línea, nosotros también tenemos nuestros proof of principles, tenemos bastantes, pero acá pues es toda una batalla diferente como buen país cuasi tercermundista.
I'm very happy to stay later if you have any questions. If you want to talk about this more, very happy to answer your questions.
Pablo va a estar aquí
The rest of the day, okay?
todo el resto del
Please,
día.
yes.
Pablo, un reconocimiento de parte del CEO, muchas gracias por aceptar nuestra invitación y gracias por venir.
Muchas gracias.